Hey everyone, and welcome to class number 4. Yeah, it's been 4 classes already of our Raspberry Pi Pico deep dive course. And let me share my screen so you can see the agenda for today. And then I totally need a teacher hat, says the chat. And then we can go over the agenda. So sharing my screen. And you should be seeing it right now, and let's make sure that I can still see the chat. This is always a challenge to figure out how to open the chat after sharing. Okay, I got it. I will try to get a teacher head for the next session, I promise. Cool. So yeah, before we get into the agenda, which is mostly about reverse engineering today, I just want to update you on a couple of things. So first of all, this is brand new, but now if you go to walkwe.com, you can just click on this Raspberry Pi Pico to start a new project. So I added this like template, and then it works out of the box. You don't have to worry about anything. Don't have to remember or copy paste an existing project link. So that's one thing. And the second thing is if you now click on the Pico, you will see this question mark that takes you right to the documentation. And that's a good spot to mention that there is hey Nekade, there is there are like 2 ways to run the Arduino code. I think I mentioned it, but basically there is like the official core, which is what we are used, and also community maintained core. And if you are writing assembly, and some of you had this issue in your homework, then you need to do one more thing. Let me show you this to you. So we had this Mech32. So if you are using the standard Arduino official Pi core for Arduino, you don't need to do anything. But if you are using the community core, either in the simulator or in your Arduino IDE, then you also need to add .thumb, because for some reason the community core it doesn't compile to ARM thumb, it compiles to the ARM instruction set by default. So just make sure you add .thumb at the beginning of your file. By the way, I think we didn't have this last week, but this week there is a proper syntax highlighting. I just added it, I think, maybe yesterday or the day before. So now if you type a valid instruction, it will be blue. Other instruction, it will be black. So just another small change to help you. And one more thing. When we implemented the Max32 last time, it was int and not unsigned int. Like that's how we define the function, and then we use this branch high. But to make it totally correct, if we wanted to use like signed integers, we needed to use BJT instead of BHI. So this is unsigned comparison. This is signed comparison. I fixed this since just changing it to unsigned it, but somebody like one of the students told me about that, so that's a good catch. Use the correct instruction that will match the signature of the function. All right, so one more thing. That was also a suggestion from someone last time. So now if you do BKPT, let's do this for a moment. Run this example. So now BKPT also print the amount of cycles. So like if I have one BKPT before this print and one BKPT after this print on it, then I can like do the difference and see how many clock cycles have passed since those 2 points. It's not 100% accurate, but for small functions, it should give you a good estimate. For the other, wow, That's a lot of comments in the chat. We'll take a look in the Q&A. And before we dive into whatever we're going to dive in, I also wanted to show you something that I found today, which is this. And this is a high-resolution picture of the silicon die of the the RP2040 processor. And I find it very interesting to see like how much space, like physical space on the die is actually spent on the SRAM, and how little space is actually spent on the processor in comparison to the size of this die. And I have no idea in silicon and how it works, but I just find it interesting. And this is taken from a blog post that was announced. No, this is taken from a blog post that was announced today, but there is another blog post telling about how they developed this silicon. So it's just interesting. If you want, you can read it later. I found it interesting, so small bonus for you. Okay, cool. So that was it for the announcement section, and now let's dive right into this reverse engineering class. Yeah, it's a reverse engineering class. So the first thing I want to show you, so we have this code, like let's open the Fibo project from last time. I really liked it. So we had like Fibonacci sequence. We don't need this one anymore in assembly. And we implemented it. It prints all the Fibonacci sequence from 0 to 15. Okay, all is great. Now, what if we wanted to see, like for this for loop, how does that compile to assembly? So for that, there is a tool called objdump that can show you the assembly code that is generated by the compiler. And that's a great way to learn how to do things in assembly, just by looking how the compiler does them. And you can run it on your own if you want. Just ask me in the Q&A and I will show you how. But if you are inside Walkly, you can F1 and view assembly, compiled assembly code listing, and then you wait for like a couple of seconds and the listing appears here. And I'm going to, a word of warning, it's long and scary, so bear with me, please. Okay, so this is the assembly listing. This is whatever the compiler generates, and you can see there is like tons of code here, 37,000 lines. It's crazy. This is everything that the compiler generates from this small piece of code. And it would be a nightmare to navigate, but luckily it also includes like snippets from the source code as comments. So I can just search for setup, and then I can find like, for instance, this line, serial.begin, it translates to this code. And basically it calls, this is like mangled C++ name, but it's Arduino UART begin. That's the method it calls behind the scenes when you call serial1.begin. And I think that the interesting thing we can do, first of all, is to take a look at how the compiler compiles our Fibo. So let's look. So this is the compiled Fibo. And if we just compare it with the source code, I guess it looks pretty much one-to-one. I don't think there should be any difference. Maybe like a very small difference in how the instructions are written, because there are like a few ways, like for instance, instead of this move R0, R4, R0, it's compiled to add R4, R0 with 0, just a different way to say the same thing. But other than that, it's basically the same. And I think a fun thing to do would be to see if we write Fibo in C, how it would compile. So let's do that. So let's create another Fibo, call it Fibo C, and it gets an N, and it's no longer an extern, it's just a normal function. And then if N is more than, let's say, 1, then it's Fibo C of N -1 plus fibo c of n minus 2. Otherwise, we just return n. So that's a one-liner fibo in C. And let's also print it in the output. So because if we don't use this function, it won't be compiled. So we won't see it in the listing. And you know, just a quick sanity, and we can see it returns the same value as fibo. And now if we take a look at the listing, it will take a couple of seconds for the listing to appear. And then we can, you know, just Ctrl+F fibo C. And yeah, you can see it has been decorated because now it's a C++ function. But like the name has been mangled. But if we compare the implementation, it's pretty similar to what we did. It's not exactly the same. We are copying the argument into R4, and I think we also did the same thing. And then we are loading 0 into R5. We are comparing the argument to 1. If it's less than 1, oh yeah, I should, or yeah, less or equal, yeah, LE is probably less than or equal 1, then we are branching here, which is just returning. Otherwise, we are subtracting 1 from R4, putting the result in R0, calling ourselves. Then we are subtracting 2 from R4, and yeah, and moving the result we got from here into this R5, and then calling Fibonacci again. And finally, we are adding R4 and R5. And an interesting thing to note, the compiler did some optimization here. It's actually not going jumping. It's not calling the function again. You can see just going back here to repeat this process once more. So the compiler did something smart. Instead of calling the function from it within itself, it just figures out that the other, like it could use sort of a loop to call to do the same call after subtracting 2 from R4, which is like the original argument value. So that's how the compiler does fibo. And what I want you to take on it, to take from this, is how easy it is to see what a compiler does. So we can learn from the compiler if we want to do something like, and we don't know how to do it in assembly, we just write it in C and see what the compiler generates. One more cool thing I want to show you. Let's say we have this, so I goes from 0 to 2, and then we are just, you know, printing I. And if I compile it, it will print 1 and 2 after printing all this Fibonacci sequence. Or, oh yeah, we need serial 1 because serial is like the USB, and we don't have that yet in the simulation. 0 and 1, cool. Now, if we take a look at the listing, you will notice that this loop has been, it actually, I don't think it appears here. Let's take a look at setup. It's inside setup. So you can see that this loop has been just translated into 2 calls to this Arduino 5 println. So this println function. The arguments are, by the way, this is like the first argument is just the dis pointer, because this is a C++ method. It needs the dis pointer of this serial 1 class, and this is like the value that we are printing, and this is the base we are printing. In this case, we are printing in decimal, base 10, and it's optional argument, so you don't see it in the code, but it's generated in the compiler. And this thing, we had a loop in the code, but here we don't have the loop. This is called loop unrolling, and that's one of the optimizations that the compiler does. And we also have a comment on the chat saying that what we have seen with Fibo is called tail recursion elimination. That's correct. Thank you, Przemek, for pointing this out. So that's another optimization. And now we are seeing this loop unrolling. And I leave it for you as a fun exercise to figure out what is the greatest value of I that will still get the loop unrolled? Like, is it 2? Maybe more than 2 we will already generate a loop, just to show you that it eventually get unrolled. If we go 100, it eventually doesn't get unrolled, sorry. If we go up to 100, then this loop will be translated into an actual loop. You see there is like this function call, and then this is where we compare the loop counter to 100, and if it's not equal, we go back here. So this is the actual loop. So I leave it to you as a nice exercise to find what's the greatest value of I that still gets this loop unrolling optimization. You can write in the chat when you find it out. Cool. So that was a really deep dive. Not deep dive. It was a really quick show of this or a quick look at how the compiler translates C into assembly. And if you want, we can do it in the Q&A. There is like all like the bootstrapping here. So you can see here at the beginning, there is like, this is the vector table that we have seen, I think, in class 2. And this is like where the code begins, the entry point. We just need to change it from 3 to 2 because of the thumb bit. So you can see the reset handler. And you can actually follow here all the code until it gets to setup if you want. You know, just read the assembly and sort of figure out your way to see how the compiler or how this code gets from the very beginning into setup. But we're not going to do it now because we have more interesting things to do. Before we move on to the next subject, which I really love, one more thing to show you about this. So we have seen this op-jump output, and there is a lot of output. So I'm going to show you another way to see how the compiler translates from assembler to C. And this is a free tool called the Godbolt Compiler Explorer. And you basically give it a piece of code, and you get the, let's zoom in a bit, you get the generated assembly code. You can choose a bunch of compilers. Specifically, this one actually generates thumb codes. Other compilers like the Sklang, I think I'm not sure they generate thumb code. Yeah, if there is still a lag, let me know in the chat. And the thing I like about this tool is that you can, just break this code into several lines, and it will color each line and the corresponding assembly code, so you can see how like this code translates to this, and like it's really easy to match the source code with the compiled code. Now, this is not ARM v6. There might be some opcodes that are not available on the PyPico, like PyPico does not implement all the thumb opcodes, only some of them. But for the most part, it should give you a good idea, and it's a great way, again, to see how the compiler translates. If we wanted to see, by the way, the actual opcodes, we could enable this compiled binary. It would also emit some garbage here, but then at some point here, yeah, we can see the actual function implementation, and we can see like 2-byte opcodes that's thumb. So this way we can see it's actually generating thumb code. But here at the beginning, you can see those instructions aren't thumb. This is like ARM, because they are like 4-byte instructions. It's not always like that. There are a few 4-byte thumb instructions, like BL, which is 4-byte instruction. But if you see like a bunch of 4-byte instructions one after the other, then this is most likely not thumb code. Like this instruction in thumb is only 2 bytes, and you should probably know that already. So yeah, that's a cool tool. I'm going to paste the link into the document. So yeah, class 4, and let's add this one as well. And with that, let's move on to the RP2040 as Persimek says, it doesn't implement every thumb opcode. It implements Cortex M0, and I think we have seen there is like this very fat datasheet, the ARM ARM for the ARM v6, and it includes the list of all the opcodes that the Pico implements. You also have this somewhere in the datasheet, I think here, and probably here in the programmer model. Yeah, and now I killed. Yeah, you have like a summary here of all the instructions that the Pico implements. And there is also like this, where was that? Yeah, I think it was here. And we have like this cheat sheet I showed last time, and it has, again, it's not one-to-one with the Pico, but it more or less corresponds with the instruction sets of the Pico. So you have the link to this cheat sheet in here from somewhere here, this one from the last class. Anyways, so now let me show you one of my favorite tools with when we want to understand code, especially assembly code, when we want to go deep. And this cool tool is called GDB, the GNU debugger. And the good news is that you can actually use it in Wokwi. That's something I worked on really hard. If you want all the details, I think there is a blog post somewhere, or maybe I forgot. Oh yeah, no, not this one. Yeah, I will put the link later, but basically a blog post explaining how I got GDB to run in the browser. That's, I think, a fascinating read for itself. It's like Linux virtual machine that runs inside your browser that runs GDB. And to start all of this, you just F1, press F1, then GDB, and you have two options, the debug build and the release build. Usually you want to go with the debug build because that doesn't include a lot of compiler optimizations that can interfere with debugging. But if for some reason you need to debug the actual file that you are running, I don't know, there are like some optimizations that are required for your code, then you will want the release build. But it's rarely useful. Usually I just use the debug build. So as soon as I open that, it will launch GDB. And if you are doing it for the very first time on your computer, it might take a few seconds for GDB to install. Also, if you see this error about no such file or directory, this is a glitch I'm still working on. Just close the window and start it again. It just sometimes doesn't download the file on time. And there we go. This is GDB. Let's zoom in a bit. So, and let's put it side by side with the simulator. So, yeah. So, yeah. Where is this simulator? One side, and then GDB the other side. Cool. So, as you can see, the simulation is stopped. It's not running. And the first thing we are going to do in GDB. That's a little mind-blowing, thank you. The first thing we are going to do with GDB is, the first command is continue, and it tells GDB, hey, continue running the program. So as soon as we do that, you can see that the simulation is running again. You can see all the output, all those, this is like the loop that printed 100 numbers, and all the Fibonacci sequence, and it works. And as soon as we want to pause, we just Control-C. And we did that. GDB tells us that the program received interrupt, and we don't have the source code for main, but right now it's inside the main function somewhere. If we had a source code, that would be this line. And usually the first thing I do when a program stops, then I run backtrace to see where I am. And backtrace just shows me the current stack trace, and we'll see it in a moment. You know what, let's continue and break again. And no, we are still in the same place, so let's try that one more time. Control-L to clear the screen. Let's try continue. Yeah, it always stops at main. It's probably because we have an empty loop and main called loop. But the first thing I want you to know about GDB is that there are like a few ways to do everything. So you can type backtrace, you can type BT, you can type where. They all do the same thing. And now that we have seen how to see where we are, the next thing we want to do is probably to see the registers. So it's more or less the equivalent of this BKPT42, but now this is proper GDB. Info registers, actually info register also works. It just shows us all the registers and their values. These are like the registers that we already know. This is the flex register. This high nibble is the flex. GDB doesn't break it down nicely. And a few more utility registers of the Cortex M0. And there is a question in the chat if we use QEMU. No, we use V86. I will just put the GDB in the browser blog. Yeah, this is the blog post. You can just, you know, if you're interested in the details, it's all there. And has a nice cover photo. And someone is asking whether you can self-host those tools so they run faster. So after the first time, it should load faster because it's cached to your browser. But if you just want to run GDB locally, you can use this project. I will also share a link. It's a bit complex, but one-time setup, and then you can use your local GDB with Wokwi. So that's another option. And of course, if you are using GDB locally and you have a PyPico, you can also use GDB with your actual PyPico. And there is like this getting started guide. I linked it in the first session, and it has a whole session that tells you how to set up a physical, another Raspberry Pi as a debugger, which is what I'm doing. Or if you have 2 Picos, which I don't, you can also use the second Pico as a debugger. So one Pico debugs the other. That's another setup, and it's all explained very well here in the Getting Started guide. So do check it out and do try it if you do have the actual Pico. I said do too many times. All right, so now our program is running. It's stuck in the loop, but let's say we want to go back. The easiest way to do it would just be to restart everything, and for that there is like monitor command. Monitor sends a command to the debugging backend. So in this case, it would send it to Wokwi. If you are using a physical chip, it would send it to OpenOCD, which is the translator that translates between GDB and the debugging protocol of the RP2040. And in order to restart the chip in the physical chip or in the simulation, just monitor reset init would just restart. Yeah, I will just refresh it so it fits the window. Yeah, now it should fit the window correctly without the scroll bar. And yeah, so yeah, now let's clear the screen. And yeah, if I'm checking the backtrace, I can see I'm somewhere in main right now. But if I type monitor reset in it restarted the simulation. And now if I look where I am, actually BT will still show me the old place, but I can tell the microcontroller to execute a single instruction, and that would synchronize GDB and the microcontroller again. So step I or SI execute a simple instruction, and we can see that we are inside the flash binary start, like the very start of this. If we take a look here, it's like this boot start. We don't see the disassembly here for some reason, because probably because the way of this binary is built, but this is actually thumb code that has the boot stage, the stage 2 bootloader, and we are now inside it. We can ask the GDB to show us the current function. So typing this as will just show us a disassembly. You see this arrow? This arrow shows us this is the next instruction that is going to execute. So basically, this is this code is boot to start. This is the disassembly. Thanks to GDB, we can see it. And we can, of course, disassemble our code as well. So if we wanted, create a screen, Control-L. If we wanted to see the Fibonacci, we can just ask to disassemble Fibo, and that's the assembly Fibonacci. And just like the listing, but it's much faster to use this tool, in my opinion, than to crawl through the endless list in this listing file. And we can also disassemble this as FiboC, the C version of Fibonacci. And by the way, you can see that some of these names are mangled. This is not too bad, but if we disassemble setup, for instance, you can see that there are like all these ZN Arduino for UART begin. It's not convenient to read it this way, so we can actually there is like a bunch of settings, so we can ask GDB to I think it's ASM demangle on, and then if we disassemble setup again, now we can see the proper method names and signatures. Same goes for FiboC. This as FiboC. Cool. Yeah, sorry about the video audio lag. I don't know what happens to Zoom today, but I hope we can still keep the pace. Cool. So that's how we can see the registers with info registers at any point in the program. And this assembly will show us the source code for, or the assembly code for any function. There is also like a list command that will show us the source code. So we can do list FiboC. It will show us a few lines before and a few lines after. Pretty useful if you just want to quickly look at a function, how it's defined. Once we have this, we have the very basics, but I think the most useful thing you can do with GDB, other than like inspecting the data, is setting breakpoints. Let's say we want to, okay, before we get into that, somebody asks about cheat sheet, and that's a great question because I prepared one for you. It's actually, yeah, did I close that? I guess I did close it. Yeah. Oh, that's not the correct window. That explains why it's not here. Yeah, so there is like this cheat sheet for Arduino EVR. It's 95% the same as the ARM, so it's very useful. You have like most of the commands that, or maybe all of the commands that I mentioned here with examples. So I will just post the link so you have this cheat sheet and you can consult it as you need. So yeah, now you also got a cheat sheet. Cool. So I think the most useful thing in GDB, or the most useful skill, is to be able to set breakpoint. And for that, we can use the break instruction. So we can tell it to break when we get to setup. So breakpoint at setup. And now we can just monitor reset init or halt. It's the same. And continue from the beginning. And now it's stopped at setup. It also shows us the line of code we are at, line 11. And we can run it line by line. If we type next, it will just run the next line every time. So next, and you can see like it ran the printf. And this is how we run the program line by line. By the way, if you just type enter, it will repeat the last command. So I don't have to type n every time. I can just type enter on my keyboard and it will execute this command by command. And of course, while we are running this code, we can print, we can of course take a look at the registers, but we can also print values, like we can print I, the loop index. We can even change things, like let's set I to 12. Yeah, maybe it doesn't like setting I. So let's not set I to 12. I think there is like an issue here with the name I specifically. But basically, we can also change variables while we are running. And Yeah. Oh, and of course, thanks for the Mark for the comment. You can also, there is help in GDB. And if that's not enough, and you need even more information, there is like this GDB manual, which has all the information that you need. That's how I learned. Sometimes it has too much information, but let me just link it so you can check it as well if you want. I would probably start with the cheat sheet though. And okay, going back to the Pico and the GDB. Okay, cool. And now we know how to set breakpoints and to run the program line by line with next, or we can also, let's see where we are right now. So we can also type step to step into functions. So as soon as I type it, I go into FIBOC, and it shows me the value of n. If I now, by the way, it's a good way to see the backtrace. So now I can see I'm inside FIBOC, which was called with n equals 7 from setup, from main. And if I further step into it and further and further and further and further, I will have a nice backtrace. Again, where is the same as backtrace? I can see like the entire backtrace here. And another useful command is finish. It just tells GDB run until this function returns the current function, and it also shows me the return value. This is 1, and then if I type finish again, it will return from the next Fibo, which returned 2. Like now you can see how I'm going up the stack trace finish. And finish. It doesn't go recursively, it just waits until Fibo finishes. And now I can see like this is, it returned back to setup from this FIBOC with the value 13, which is going to be printed next. And I can also step into printf, or maybe not. Yeah, it should be able to, I should be able to step into printf. I don't know why it didn't work. So there is next, there is step, there is finish to return from the current function. There is also like step I, which steps a single instruction at a time, and it's a bit hard to see what's going on here, but you can see I'm inside this Fibo. If I will disassemble, it will show me where I am in Fibo. That's our Fibo, and you can see it's running. Let's finish this and yeah, and go again into Fibo, single instruction. Now I'm in Fibo at the beginning, and I want to show you another useful command. So at the beginning of Fibo, we are going to push these values to the stack. And if we type info registers, we can see that we are going to push R4, R5, and del R. So that's 9, 15, and this value 399, and we can use the x command, examine, to print out the value of the stack. So x for x, sp is the stack pointer. You can see the value here, and this is what we have, the 4 values that we have at the top of the stack right now. It's actually, let's make this a bit bigger so it's easier to see. So it's 0, 0, 0, and this value. You know what? Let's even print 8 values from the stack. So examine, print 8 entries in hexadecimal, 8 words in hexadecimal. So this is what we have right now at the top of the stack. And now I'm going to execute a single instruction to go past this push. So single instruction, or step si, or step I. And now we went to this address, which is the second instruction. And I can also already, I can print the SP again. And now you can see how those lines were shifted down the stack. And we have those new items, which are 9, 15, and 399, which were the values of LR and R4 and R5. So this command is useful X to take a look at any kind of memory. We can even look at like xFibo will show us like the the binary code or the machine code inside. Like, let's do it with bytes. The bytes that are encoding the instructions for FIBO. So that's how we look at the memory, and specifically, it's a very convenient way to take a look at the contents of the stack. One more thing I want to show you is a command called, I think we have seen print. Print can show us values of registers, so we can print a single register, and we can also print variables. I think we have seen that. Let's finish. And we can print any symbol in the program, so we can print FIBO. It will tell us what's the address of FIBO. We can even do calculations, so we have here I, we can print I times 2. And we can also use print to read memory, so that's a less convenient way to, like I can do probably if I typecast FIBO into a pointer and print its value, it will show you, it will show me the first 4 bytes of the FIBO function as like unsigned integer. I can also use this /x to tell it to print in hexadecimal instead of decimal. And again, if you do help print, you can learn about all the options, or again, help x, about all the options for those commands. But I want to show you like some more interesting things that we can do. So one of the things we can do is actually call functions from our code. So for instance, where are we right now? So one of the things we can do, we can just call FIBO 15. Oh, yeah, and we should tell it that FIBO returns an integer, and it will print us the value of FIBO 15 or 20. It takes time because FIBO is like a deep recursion, and I think if we actually zoom on the browser, it will be faster. So it actually runs the code on this in the physical chip or in the simulator while you write code. Doing this may mess up with the code. I don't know if it did this time. No, it still runs. That's great. But yeah, sometimes this can mess up with the code. But I want to show you a few more interesting things we can do with GDB that make it more powerful. Do we have? Yeah, we have some LEDs here. Let's change the code so that they are, let's say, initialized to all be output. So for int I2, I less than 8, I++, and then in mode I output. And now once we have them as outputs, we need to restart GDB because the file is changed, so it won't be synchronized with the debugging symbols. So I will restart GDB. Also, let's no, we don't need to do anything inside loop for now. Restart the GDB, and yeah, you see it loads it from the cache, so it's really quick after you did it for the first time. And let's set up. Another way to set up breakpoints is with tbreak. Tbreak is temporary breakpoint. So set up a temporary breakpoint at setup. And now if we continue, it will stop in setup. And actually I want to go all the way to loop. So let's break in loop. And now the code is running. We have set all those pins to output, but we can actually light up those LEDs if we write to the correct memory location, just like we did in the first lessons. We have this, or in the second, I think it was the first lesson where we did it. If we go to this SAO, where are you? It was here. There was like these SAO registers that allow us to control the GPIO. So if we go to SAO, there is like this GPIO out. So it's at offset 10 of this one. So let's go back to the GDB. So we can do something like set this address plus 10. Yeah. So let's set it to FF. And as soon as I hit enter, you can see all the LEDs went faintly on. The reason they are faint is that we actually need to run the simulation. So if we execute one instruction, they will be updated. The reason those two aren't updated, by the way, is that they are used by the serial peripheral. So they are not really, if we set it to 0, it should, yeah, they are not really controlled by the SAO right now. So that's why they are not updating. But yeah, you can like use the set command to write to registers or all sort of stuff. And then another cool thing you can do, you can sort of stub functions. So let's say, let's reset init. So let's say I want my Fibonacci, I want to replace its implementation. I can do something like that. I can say I want a breakpoint on Fibonacci. And then I can define a set of commands that will run whenever it hits this breakpoint. So I do commands, and then I tell it, first of all, whenever you get into this function, we know that the return value is in R0 because that's how things work. So I want you to set a return value to R0 to 22, and then instead of executing the function, we know that the return address is in the link register. So we can say set pc equals lr. And these are GDB commands that will just update the value of the PC register into the value to the value of lr, the return address of the function. And finally, I want also to continue the simulation, C or continue, and now we have defined a set of commands that will run whenever this Fibonacci is called. Let's see if this works. So if I continue, we can now see that it hits the breakpoint every time Fibonacci is called and our code is executed and returns 22. So it's super useful if you don't. You just need to quickly replace a function with a mock value to quickly test something or something like that. Yeah, I also think that's super cool. One more thing, there is a better way to use GDB. There are a few better ways. One of them is to use the TUI, text user interface. So instead of like only seeing the current line of code, I can do TUI enable. And suddenly I have this view where I can actually see the source code side by side with my my GDB prompt. So if we are going to monitor reset, actually monitor reset init and tbreak in setup and continue, we can actually now run line by line. We can even improve this. Oh, we got into UART begin. I didn't want to go there, so finish should help. Yeah, now we are stuck in this Fibonacci. Yeah. So another cool thing we can do, we can actually split the screen. So we have the source code. Let's restart the simulator. Break setup. Let's monitor reset init, and then we can continue. And then let's, by the way, you can also see the breakpoints I've set there marked here. I can do layout split, lay split or layout split. And now I'm seeing the assembly code side by side with the C source code. So I can now step a single command at a time with next, and it steps over a bunch of instructions. Or I can, you know, step instead of like doing one command at a time, I can also do like a single instruction by writing next I. So now it will move to the next instruction in the assembly window. And by the way, there is like all these variables like underscore serial. So you can print those values as well. Now it's not here, storage. Yeah, and you can see the print function can actually print complex data structures. I think we had serial before. There is even a better example to show you that. So there is like this, yeah. Let's take a look at a real program for once. There is like this code from Anderson. yeah, you did this demo yesterday with the keypad and the Pico. Basically, whenever you press one of the keys, it lights one of the LEDs and 0 clears them. It has some nice logic here. I will paste the link if you want to check it out. That's not the right place here. Yeah, so there is the link. And yeah, what I want to see here is if we open this with GDB and use the print command, missing L file, run it again. I hope to fix this glitch later this week. So so now let's break inside loop. So it runs everything until loop, continue, and we are in loop. And you see we have a bunch of where we are in loop inside probably main. You see we have a bunch of variables here, and we can print them with print, like print keys. It will print the value of keys. It knows it's an array with 4 items. But I think something more interesting to do would be to print something like a keypad, which is actually an object, and we don't really know what's inside it. So let's do it. And as you can see, GDB knows about the types of objects that you have in the code, and it can print all of those fields and nested fields. And that's super useful when you are debugging code, especially code that you are not familiar with, and you want to see how it changes, how the data changes over time. Cool. Let's see what else do we got with GDB. Okay, so one more nice thing that I want to show you is like we can probably find a way to do it here. Yeah. Let's say I wanted to print a variable whenever I hit a breakpoint. So instead of stopping at a breakpoint, I just want to print the value of the variable. So I can use the dprint, which is there are a few ways to do this. There is also a display command, but dprint I like it. dprintf actually. I tell it where I want to print. So let's say I want in keypad Pico at line 48 where this switch happens, and I want to print key is just %d, and then I can print the value of key. And no, it didn't find the source file. Interesting. Oh, I think it's called sketch.ino. Yeah, it's called sketch.ino. I can also like list the loop file to see that, the loop function to see, line 48, Okay, and now I'm going to hit continue, and nothing happens until I press on a key, and then you can actually see the value of this variable in this line. So this allows me to print any local or global variable in any location. You can actually see that this is posed by the GDB when it hits this breakpoint, and then GDB reads the value, prints it here, and you can continue interacting with your program. So Mark, just relating to the questions on the chat, GDB is not running on a server. GDB is running in your browser, taking 64 megabytes of RAM. So if you need this feature, I can definitely let you customize the startup script from GDB for GDB. Just because you asked, we can go from GDB to the shell, and then you can explore this virtual machine. There is like /mnt with all those source code that it downloads from the simulator, and also like this shell script that starts GDB. So if you want, just go run it and explore this virtual machine that runs in your browser. Now you know how. Yeah, with WebAssembly, and again, I don't want to dive into the details right now, but I also find it fascinating. So you have like this running GDB in the browser, which goes into all the details that you can check out later. Before we sign off, I just wanted to quickly show you a few cool things we can do with MicroPython. So GDB is a great tool, and I could go talking about it for hours. If you want to try running GDB locally, you can also F1 and download ELF with debug symbols to your machine. This will download the ELF file that you can download locally in GDB and also upload to your PyPico and do the debugging on your machine with your GDB and your physical PyPico. If you want, let me know in the Q&A and I will show you how to do it. We have just scratched the surface. GDB can do a lot more, and it has even got a Python support, so you can script it in Python. We are not going to go into that, but you can even enable it in the WebGDB. If you want, ask me later, and I will show you how. So there is Python support, and you can like write code in Python that executes on breakpoints and does all sorts of stuff. And that's a good opportunity, speaking of Python, to talk about our next subject, which is MicroPython. So as you probably know, MicroPython also runs on the PyPico, and this is something I just added yesterday, so now you can run it in the simulator, which gives you a good opportunity to explore the Pico internals with MicroPython. So I will just share the link so you can play with it later. And one of the cool things you can do with MicroPython is just import machine and then just read random stuff from the memory. For instance, mem32 is like all the machine memory. We can just read what's it, address 0. That's probably part of the boot ROM for the Pico. Yeah, we can just read the oh yeah, it has to be aligned. We can just read stuff from the memory. We can also write stuff for the memory. So for instance, I'm going to connect an LED here. Let's add an LED, just so it's a bit more interesting. GPIO2, and the cathode goes to the, no, not here. The cathode goes to the ground. Yeah, cool. And now, did I write a training? Yeah, my bad. I will fix that. Okay, so now let's just import pin from machine, or from machine import pin, and configure this pin 2 as an output. And I'm going to run it, and we'll do the same thing that we did with GDB. We are going to machine.mem32, and I already remember this address. Just set this to FF, and we wrote directly to the SA row register to turn this LED on, and we can turn it off. So everything that we did with the direct register access in the first lesson, you can also do now with MicroPython without re-uploading your code. It's super useful if you want to experiment on your own PyPico, on the physical one, without like re-uploading the code all the time. You can also do this with GDB, of course. That's another way. And there is also this cool thing where you can actually use assembler inside MicroPython. So there is this example. This function, for instance, will just return, you can guess, 42. So if we print fun, then you can see, it has to be moved. So the RP2040 doesn't support all the thumb instruction, but move R042 will return 42. Now, I'm going to give you this link. So if you want, you can also dive into this, like the inline assembler, and there is also like this reference with all the instructions. Not all the instructions are supported. It's just a subset. It's a bit limited, but it's another cool way to experiment with assembly on the PyPico without compiling the code all the time. We can get arguments like R0 and R1. They always have to be called this, and then we can, add R0, R0, R1, and then we can fun56 will return the sum of them. And an optional, totally optional homework for you would be to implement Fibonacci here. And I'm already warning, it's not trivial if you try to do it. Then, well, maybe you shouldn't read the docs because they have the answer here in hints and tips, but you should probably take a look at the hints and tips because there are some gotchas. One cool thing we can do is we can actually debug this with GDB to see what the where is the GDB? Yeah, to see what this fun function looks like. The thing is, it's pretty challenging to find the address of fun. There are a few ways to go about it. One way to find the address of fun would be to set a breakpoint there. The third thing is that the MicroPython assembly doesn't have the PKPT instruction, so we can cheat. We can do something like data, write the data, and then go to the data sheet and find the opcode for the instruction. Where is PKPT? This is PKPT. So this is the opcode for the instruction. The I bytes are just these bits, and then this is the integer value that we have after it. So if we go here, we can just try our luck and have those. This should insert probably a breakpoint. Let's try that. Shifted by 8. So let's see if we are lucky. And running it, and whoop, it breaks. But I think GDB isn't synchronized. Yeah. But we can see this is where the breakpoint is, at this address. And now if we disassemble here, and GDB has no symbol, so we need to tell it how long to disassemble. So we can see this is the BKPT instruction, and this is the adds. And we can see that actually we can go a few 2 bytes back. So this is the assembly code that GDB generated for our function. So you can see like it added this push at the beginning and this pop to return. So sorry, not GDB, MicroPython. So MicroPython basically adds this before all of your functions, saving the values of those registers, and then it doesn't save the higher ones, and then restoring them at the end. So if you write your own assembly functions, then you probably want to know what it adds. And cool. We could add 42. It doesn't really matter if we just want GDB to breakpoint. It doesn't matter the value. The value 42 is useful if we want to print it in the console. Another cool way to find the address of fun would be just move R0. We can move the value of PC to R0. And then if we print, it doesn't really matter what we give it. Let's just do it as hex. Yeah, you will see it's pretty much the same address. It might have moved because we have changed the code, but yeah, now if we just disassemble here, you should see this function. This is actually the address. When you move PC into another register, it's always the address of 2 instructions after. So it's actually the address of the end of the function. But that's another cool way to find the address of fun. And this is like just, fiddling around in MicroPython. There is a lot more you can do, and optional, totally optional homework. If you want, just try to run, to write Fibonacci or your existing homework, GCD and Square. Try to write them in MicroPython assembly. You can pass an array, and it will pass the. It's a bit complex what will happen when you pass an array, but basically R0 will get the address, the memory address of this array, and those elements will be let's just print them. Actually, never mind. You can experiment with it later if you want, or ask in the Q&A. But there is like a lot of stuff you can do with this. One use case, one cool use case, which I used it for in the past is, let's go back to this window. Too many windows already. Yeah, so if you want, you can read it, how we use like stuff like the inline assembly to optimize a critical piece of MicroPython code a few years ago. I think it's a fun read. So yeah, you got a lot of stuff to read today. So as well, again, I'm not going to give any homework. It's all optional if you want to play around with MicroPython and implement some of the code in of your assembly functions in MicroPython, then go for it. As usual, we had a pretty intense session. The next class is going to be the last class. We are going to talk about PIO, programmable I/O, and it's going to be at least as intense, so please prepare yourself. I'm going to tidy up this section a little after the session, so split it up to maybe blog posts and I don't know, we'll see. Thanks everyone for joining me for this session today, and I hope that you will have a great week. Keep experimenting with MicroPython and all like the internals of the PyPico.